Hello and welcome to the HamCorp Guide to GTNH particle physics. In this video, we will go over the upcoming Large Hadron Collider multiblock, which will be added to GTNH in 2.9. This multiblock was designed and implemented by me, well mostly me, with a lot of help from many members of the dev team and GTNH community. That's right, the LHC is literally HamCorp. You can try the LHC and all the other new 2.9 features now if you play on the dailies. Please do that and find bugs for me so I can fix them. Thanks. At the time of recording, 2.9 is still in development, and the LHC and Beamcrafting still require balancing and bug fixing. Check the pinned comment to see if changes in how the system works have been made since this video. Minor balancing changes are not going to be covered in that comment. The LHC is a replacement for the old compact cyclotron, or Comet, which will be removed. The LHC and Beamcrafting multis use the existing beamline mechanics and are actually compatible with the beamline multis. In fact, you may even be able to use the LHC to do beamline recipes, but that's not something that's been extensively tested at the time of recording this video. I can confirm that it's possible, but not if it's actually viable in the actual game. The beamline is technically still optional, but considering the LHC is not, I expect to see a lot more beamlines. The LHC will be the new method of obtaining quark releasing catalysts. Yes, longtime HamCorp fans may be making the link now. This multi was indeed born entirely out of me being overly pedantic about particle physics. Anyway, the LHC now gates grade 8 water. The Beamcrafter, which can be used before you get an LHC, now gates unknown particles and the quantum anomaly. All recipes that formerly used particles as items now use particles as beams. Particles no longer exist as items, with the exception of the unknown particle. First, let's cover the basics of particles in GTNH. Particles in beams travel as packets, similar to the research station computation packets. Particle packets have 4 attributes: type, energy, amount, and focus. Type is the type of particle, so electron, muon, photon, and so on. Energy is the energy of the particle in electron volts. Amount, which is sometimes sort of inconsistently called rate here and there, can be interpreted as the number of individual particles in the packet. This is what determines crafting speed in the Beamcrafter and is the quantity you want to maximize. Focus is not relevant for the LHC and Beamcrafting, but it's a quantity that represents the collimation of the beam. This matters for beamline, but we will completely ignore it in this video. Next, let's talk about how the LHC actually works. I will continue based on the assumption that you have read the tooltip for details. The LHC takes any charged particle as input and generates output depending on 1. The energy of the collision, and 2. Which module you draw outputs from. The LHC has 2 modes, accelerator and collider. It cycles once per second and automatically switches from accelerator to collider when the player set acceleration cycle count is reached. In the interface, if you click this button, you are able to set 2 values, the target beam energy and the acceleration cycle count. Once you set these and turn on the LHC, it will start accelerating the incoming beam. This input beam cannot have any of its 4 parameters changed during operation, or the LHC will shut down. Using the incoming beam's values as the starting point, the LHC will accelerate the beam in accelerator mode, meaning the beam energy increases once per cycle. If the beam energy reaches the player's set target energy, further LHC cycles will instead increase the current beam amount. But how do you know what target energy to set? Well, the beam energy serves one purpose: adding particle types to the pool of potential outputs. If you have an accelerated beam energy of E, then the collision energy when particles collide is 2 times E. The types of particles that can appear in the outputs now are simply all those particles whose mass is 2e or lower. So if you're targeting a particle of mass 100 gigaelectronvolts, then set your target energy to at least 50 gigaelectronvolts. Then the collision is 100 and you can get these particles. There's no benefit to increasing energy beyond what you need. Also, not all particles can appear in all modules. Each LHC module can only produce a subset of particles. You can see this in NEI. The power draw of the LHC can be very high, since it increases quadratically with time and it also scales with beam amount. That said, I have done an analysis of how the resulting crafting speed in the Beamcrafter scales with the power draw, and I found that it's best to do as many cycles as possible. The more cycles you do, the closer you get to perfect overclocking. Details of this analysis are in an optional advanced section later in the video. Okay, that was a lot. Let's talk about how to use these particles. The Beamcrafter is a multi that takes fluid, item, and particle inputs. The craft begins as soon as input items and fluids are detected. The machine then waits for particle inputs, which provide progress to the craft. No particles means no progress. The recipe does not shut down if the particle beams are interrupted. NEI shows the cumulative beam amounts required for the crafts, and energy is consumed constantly while the craft is going. Note that at the time of recording, the Beamcrafter does not work with the crafting input buses or buffers. You don't really need them though, since there's not that many recipes and your processing is going to be limited by the LHC rates anyway. Also, the Beamcrafter can buffer particles, but it's only able to accept particles while a recipe is running. This may be changed to allow constant buffering at all times, but for now this is how it's going to be. Just going to quickly mention these because they exist, but they're all fairly easy to understand by reading the tooltips. The beam mirror allows you to turn a particle beam by 90 or 180 degrees. The beam stabilizer acts as a small buffer, allowing you to make an intermittent beam of high amount a constant beam of low amount. And the beam splitter allows you to split a mixed stream of particle packets into 4 separate configurable lines. Okay, and here's a little bit of fun stuff for the nerds in here. I know you're out there. I said before that the LHC overclocking is a bit weird and it's kind of its own thing. So if you're interested in finding out how it actually works, this is how it works. We've got 2 equations, r equals r0 a to the n, and p equals rn squared. R is the accelerated rate, the rate with which you do collisions in the LHC. R0 is the initial rate, the input rate. A is the multiplication factor, which currently is 1.1, but that might be changed for balancing reasons, so I've just left it as A. N is the cycle count, and P is the power draw in amps of UV. In these 2 equations, you can solve for N in the bottom one and plug it into the equation in the top. And then after a bit of simplification, you get the base relationship, which is this. Pretty ugly. There's not really much I can say with just this equation, so we ask the question, what happens if we overclock? Remember that R determines crafting speed in the Beamcrafter, and P is the power. You can't really overclock the LHC by increasing the energy hatch. What I mean by overclock in this case is running more cycles, because the power draw is going to increase. So the question becomes, what happens if you run enough cycles that the power draw has increased by a factor of 4? In other words, if P becomes 4P, then what happens to rate? And I declare that R becomes K times R. And the question is, what is K? For a normal multi-block, K is equal to 4 or K is equal to 2 if it's perfectly overclocking or if it's not perfectly overclocking. But in the LHC case, it's a little more weird. So we transform P to 4P and we transform R to KR in the base relationship, and then we get the overclocked relationship, which is basically the same thing, but P has become 4P and R has become KR. This still isn't really enough to say anything. So what we need to do is compare the 2 relationships. We compare the overclocked relationship with the base relationship by taking the ratios of the left-hand sides and the right-hand sides. We get this equation. After a bit of simplification, a lot of stuff cancels out, and we just get a relationship between K and R. You can try to solve for K, but it's not gonna work. You need a Lambert function and stuff, it's not worth your time. So just plot this implicitly, and then we can draw some conclusions. This is the plot, where y is K, and x is r over r0. And as you can see, it is very weird. Keep in mind that normal multi-blocks just have a constant y equals 2 or y equals 4 line. But the LHC has something that changes with time, basically. As you run more cycles, the overclocking factor improves. And in fact, it's worse than a regular overclock until you get to about 5 times the beam rate that you started with. After that, it's as good as a regular, and then it continues to increase, but not forever. It asymptotes to a perfect overclock. I tried to zoom out a bit here, but it's really not obvious. You have to do a lot of cycles, like an unbelievable number of cycles to actually get to a perfect overclock adjacent overclock factor. This is something I may tweak as well, because I have... Actually, this is a homework exercise for you if you're interested. Let me state the problem clearly. Introduce a constant c, which is a tunable parameter, which I can set, which determines the asymptotic value of the overclock in the large r over r0 limit. Basically, find a new equation or new pair of equations that lets me choose what the asymptote is. The equations I have right now asymptote to 4, but if I wanted to asymptote to 16 or something, what would the equations have to be? That's a fun little question. It's kind of hard, but I figured it out. And it's really, really ugly. Here's the answer. Spoiler alert. It's really ugly. Anyway, that's my analysis. I hope you found this guide helpful, and I hope you enjoy the LHC. And if it's not fun, let me know, and I am more than happy to change how it works so that it is fun. That is the most important thing, even more than realism, as much as it hurts me to say. Anyway, enjoy. See you next time.